Dark energy, the mysterious unknown entity which permeates all of space, makes up 68% of the universe's total energy. Despite being such a large proportion of existence, we still can't directly detect it. An international group of scientists is trying to map dark energy in our night sky. But how do you map something that you can't see? And what precisely is dark energy? I spoke to Joe Zuntz from the University of Edinburgh, who is involved in the project.
So we've known for about 20 years now that the universe is expanding, all the galaxies are moving apart. What we found about 20 years ago was that they weren't getting pulled back together, they weren't slowing down like you'd expect, they're actually accelerating. So that's extremely weird. If you threw a ball in the air, you would expect gravity to pull it back down towards the ground. And we always assumed exactly the same thing would happen in the cosmos. That's not happening. The distant galaxies, they're accelerating. They're getting faster and faster. So the nickname for that phenomenon is dark energy. As far as we can tell, some kind of thing that operates in opposition to normal gravity.
How do you look for dark energy then?
So we can't see it directly. All we can do is look for the effects it has on other things. There's two ways we can kind of search for this, the effects it has. One is about how the universe is expanding, and the other is trying to measure how structure in the universe is growing. And that's what I work on. And there's a bunch of different ways of doing that, all to do with the structure in the universe. So how we go from the beginning of the universe, which is very, very homogeneous. So that means the same everywhere. The modern universe has, huge galaxies, clusters of galaxies with loads and loads of material in, and then vast empty spaces between them. So how we got between those two situations is how structure has grown, how gravity has pulled matter together to form galaxies and clusters.
How have you measured that then?
It's called lensing. So we've known for a very, very long time that gravity bends light. If you had a laser pointer in your hand and you point it out into space, it would be bending down under gravity. You need an enormous amount of mass to make this effect detectable because light goes so fast. The only way you can do it is either having one enormous mass or having lots and lots of mass over vast distances. So what we're trying to do is measure how the gravitational fields, how gravity from all the different masses all throughout the universe is bending and distorting light from the distant universe. The current project that about 400 people around the world are working on is called the Dark Energy Survey. A big part of this project is measuring this lensing effect across about an eighth of the entire sky.
How do you trawl through an eighth of the sky?
In that eighth of the sky, in the long run, we're going to measure about 100 million galaxies. And so far, we've got about a third of those in place. And we are doing this with a computer. So we have to do it with a computer. And what we're doing is measuring the shapes of these galaxies.
Dark energy causes galaxies to spread out. So by measuring a galaxy shape, you can see how much dark energy has caused an individual galaxy to expand. Because light from distant galaxies has taken millions of years to reach us, we can see if galaxy shape, and therefore dark energy, has changed during time. To accurately assess the shape of galaxies, researchers first need to know how much gravitational lensing has distorted the image of the galaxy we see. By trawling through 100 million galaxies, they can accurately see if dark energy has changed through time. This takes a lot of computing power.
The general way we've normally done is to find one massive supercomputer, a computer the size of a room or a small house. And that works pretty well. But the thing we've been trying recently is a kind of a slightly different approach. So there's a nice connection here, which is that if you've heard of CERN or the LHC in Geneva, so the big old atom smasher system there, it turns out they have a very similar kind of computational problem, which is they have to analyse hundreds of millions of collisions. So they smash particles into each other and they have to analyse what comes out. And what they developed between 10 and 15 years ago was a system called the GRID, a bunch of different network computers. So computers still bigger than the ones you might have on your desk or your laptop. But the idea is all different universities and institutions all around the world have medium-sized computers that are networked together by this GRID system. And the idea is that you can just submit your problem and it shuffles it off and finds a place to run it for you. So it might be that your data is sitting on a machine here in Edinburgh and your computer program is sitting on a machine in Cambridge, and it knows how to connect these things together and pull them all together and run your problem.
Do we see any traces of dark energy yet, or is it too soon to say?
What we'd like to know is how dark energy is changing with time. The baseline theory we have is where it's a constant. So it's the same in all places in time and all places in space. So far, we've not seen anything that kind of disagrees with that so far. That's the big thing we're all looking for. Anything that would say kind of either evolution in time of this acceleration or different acceleration in different parts of the universe. But no signs of those yet, unfortunately.
What's next then?
The next big thing, which we're all really excited and looking forward to, is called the Large Synoptic Survey Telescope. And this is going to do an enormous enormous, much, much bigger survey, which is going to view about half the entire sky. So almost the entire southern hemisphere is going to be observed by this new telescope, which is being constructed in Chile right now.
How much is this going to cost?
Over the course of about 20 years, from the very beginning of development to the very end, it's going to cost so hundreds of millions of dollars, so maybe $500 million, something like that. So it's an enormous amount of money. It's very kind of the public and the government to fund this kind of thing. But we're hoping to, really pull out all we possibly can from this and really learn more about how the whole universe has been evolving till now and how it will evolve in the future and end.
The past, present and future of the universe, all for $500 million? Seems rather cheap to me. That was the University of Edinburgh's Joe Zuntz.